All right, so in this one, we're just going to go through and look at a couple of practice problems related to the material in chapter 16. So looking at acids and bases and the equilibrium. And for the first one, even though it's number 4 here, but for the first one, we just want to, for each of these different equilibrium reactions, identify on the left-hand side of those two reactants, which one's going to be the acid, which one's going to be the base, and we're looking at Bronsted-Lowry. So we're thinking about acids as the proton donor, bases as the proton acceptor. And then on the right-hand side for the products, kind of the same thing. It's just now we're going to be looking at the conjugate acid, conjugate base. And with this one, as well as all of the other questions we go through here, I'm just going to, as usual, continue to work through them. So after I put up the slide for each of them, definitely pause it so you have time to kind of work through it on your own, and then you can unpause it just to see how you're doing. But with the ones we're looking at here, when we're looking at assigning the acid-base pairs, essentially what we want to do is look at both sides of the reaction and see of those formula which one looks similar, because with these Bronsted-Lowry acids and bases, the only thing that's going to change is either losing H plus or gaining it, depending on if it's the acid or the base. But the formulas themselves are going to look very similar in that case. So if we look at the first one, for instance, and what I'll do is, so we'll have it set up like this just so we can kind of see. So A is going to refer to acid, B is going to refer to base, and then the C is just conjugate. So we've got in purple acid going to conjugate base, and then in red we'll have base going to conjugate acid. And again, we just want to think about which one's gaining that hydrogen. If they're accepting that proton, they're going to be considered the base. So in this case, water is going from H2O to H3O plus. It's acting as the base. And then the HBRO is losing that proton. It's going to BRO minus. So it's acting as the acid here. And then just looking at the reactions with these pairs, we're going to have an acid on one side, the conjugate base on the other, or vice versa. We'll have the base on one, the conjugate acid on the other. So when we look at the second one, we need to do the same thing. In this case, Hso4 minus and Hco3 minus could both lose a hydrogen, or it could gain it and go back to the neutral molecule. So when we're looking at it, we want to see HCO3, so that bicarbonate is going to carbonic acid. It's gaining that proton. So we're going to see HCO3 is going to be our base, meaning carbonic acid is going to be our conjugate acid, which means we'll have just the opposite there for the other two. And then finally, HSO3 minus with the hydronium ion. The hydronium ion in this case is going to water, so it's losing that hydrogen. So the hydronium is going to be our acid. The water is going to be our conjugate base, which means SO3 minus going to the sulfurous acid is going to be our conjugate, or is going to be our base to our conjugate acid there. All right. And then looking at the second one we have, in this case, we've got essentially 4 different solutions, and we want to use that one piece of information we're given to determine the rest of or fill out the rest of the table, and then ultimately determine if it's going to be describing an acidic or a basic solution. And with this, there's a couple different ways we could approach it. We could think about pH is going to be the negative log of the hydrogen concentration, or if we rearrange that, we can solve for the hydrogen ion concentration in terms of pH. And then with these, we'll have similar formula, the exact same formula essentially for hydroxide and POH. So I'm not going to rewrite those, but we would just have POH in terms of pH, hydroxide in place of hydrogen. But those formula themselves are going to be the same. And then we'll also have 14 is equal to pH plus POH. So we could use these formula. We could also use the water KW. And then remember, KW itself is going to be equal to 1.0 times 10 to the negative 14th. So we could use any of these formula. And with it, I'm not going to go through and show how we could actually plug this in. But for the first one, for instance, since we've got the hydrogen ion concentration, we could use that concentration, and we could use, let me change the color here. We could use that formula to determine what the pH is going to be, we could then use this formula to determine what the POH is going to be. And then we could use essentially this bottom formula, but in terms of POH and hydroxide, to figure out what the hydroxide concentration is going to be. Or we could have used the KW equation, because we know what that KW is equal to. In this case, we know what the hydrogen ion concentration is going to be. We could then figure out what the hydroxide ion concentration is going to be. And then we could use, whoops, not that equation. We could then just use this equation for both of those ions. It's just for the POH, we'd plug in the hydroxide concentration. So like I said, depending on exactly how we work through these, we could use these equations in sort of different orders. Ultimately, we should wind up at the same place. So I'm just going to show the answers on the next one. And then with the final column, acid or acidic or basic, just remember less than 7 is going to be acids in terms of pH. Greater than 7 is going to be the bases. So those first two are going to be describing acidic solutions, since they have pHs in the 2 and 5 range. And then the bases will be the second two, just because those are both above 7 for the pH. And one way you can remember that is just acid comes before base in the alphabet. And we're going to see the same thing in terms of the pH scale. Acids are going to be the low end, bases are going to be on the high end. All right, and then with the next one, now we've got a series of ionic substances, and we want to determine if we were to take these and place them in water, what pH would that, or not exactly what specific pH, but what would the solution result in terms of acidic, basic, neutral. And there really is a fourth option with unpredictable, where we would need to know specific information about the Ka and the Kb for those ions, so we could actually see sort of which one takes precedent. But for each of these, see if you can determine what type of solution would result. And for it, you want to think about how each of those ions is going to interact with water. Because if it's a conjugate acid or a conjugate base of a strong acid or base, we're going to see that it's not going to affect the pH at all, so it'll stay neutral. But if it's a conjugate acid or base of a weak acid or base, then it will impact it. So looking at these four, what we're going to see is the first one is going to be neutral, because if we look at calcium, it's going to be part of calcium hydroxide. That chloride is going to be part of HCl. So if we think about, for instance, how each of these will interact with water, what we could have happen, and we'll really wind up needing 2 of those waters. So this is going to be an imbalanced formula, but we'll still be able to see what's going on. We really should have 2 waters there. But for this one, the reason we're going to see that this is going to be a neutral, or have no effect on the pH with this ion, is because if we had that calcium ion react with water, we'd expect to form calcium hydroxide, and the hydrogen ion would that get freed up, because that hydroxide is getting taken from the water. But since calcium hydroxide is a strong base, this isn't actually going to form. We would just technically have calcium ions and then hydroxide. So that hydroxide and the hydrogen would really just form water. So we're not actually going to see a reaction. We're just going to have that ion stay dissolved. And we would see something similar with the chloride ion. It's just in that case, we would form HCl and hydroxide on the right. But since the HCl is a strong acid, it's still going to stay dissociated, and it just won't affect the pH at all. For the second one, though, in this case, we're going to see that this is going to be unpredictable, because both of these ions are going to affect the pH. So with the ammonium ion, in that case, we'll just form ammonia, and then hydronium ion, whereas the fluoride ion, the conjugate base of the weak acid hydrofluoric acid, is going to affect the pH, because we'll form some of that weak acid hydrofluoric HF, which is then going to essentially free up some of that hydroxide from water. So we're going to see that that's going to increase the pH. The ammonium would decrease the pH. So in this case, this would be an unpredictable salt, just because we would need to know information about the Ka for ammonium. We would need to know information about the Kb from fluoride, just to see which one's going to produce more in terms of hydronium versus hydroxide to actually determine what the pH is going to be. And then with the next one, that bromine is going to be part of HBr. So it's going to be the conjugate base of a strong acid. It's not going to affect the pH at all. But the zinc plus water, and we really should have two of the waters. Whoops, we'll have double arrow, zinc hydroxide plus 2H plus, oops. So we produce more of that hydronium, or that H plus, same thing. So we're going to see that the pH is going to increase. So far we've got neutral, unpredictable, acidic, and then we'll see in this case, that should be basic B, because the potassium hydroxide, or the potassium is going to be part of potassium hydroxide, so nothing's going to affect the pH there. It's going to be the conjugate acid of that strong base. But with the sulfide ion, we'll form Hso3 minus plus hydroxide. So we'll see that the pH is going to decrease there, or increase there, because we're looking at the hydroxide ion in this case rather than the hydronium or hydrogen. But again, with these ones, if the ion is part of a strong acid or strong base, we're going to see that it's not going to affect the pH at all. If it's part of a weak acid or weak base, that's what we'll see the pH change. So looking at these four, again, the first one neutral, then unpredictable because we don't know which one's going to affect it more in terms of ammonium versus fluoride, and then acidic and basic just for the second ones, or the second two there. And remember, with the acids, we're going to see a lot of the metals are going to be considered acidic because the metal ions only form a handful of strong bases. So that's why things like zinc and the transition metals in the middle are going to give us those acidic solutions. And then looking at the reaction we have here, calculate the pH of 0.75 molar solution of aniline. The base dissociation constant is given to us. And for this reaction, since it is since we're looking at it in terms of a base, we can just use that Kb. If we were looking at the conjugate acid, then we'd have to convert that value using Kw, but we can just use the Kb. And what we can do is just create an ice table. So we'll have ICE. And with it, we can ignore the water just because that's not going to factor into the equilibrium expression at all because it's a pure liquid. So we'll have 0.750, and then we'll have none of the products initially. So we'll see plus x, and then minus x. But for this one, since Kb is so small, 10 to the negative 10th, this is going to be a reactant-favored reaction. We're going to have very little of it move to the product side. So in terms of the equilibrium concentration for that reactant, we can essentially just ignore the negative x because it's going to be so small compared to the initial concentration. So when we go through and actually set up our calculation, we'll have that Kb value, 4.3 times 10 to the negative 10th, and then it's products over reactants, so we'll have x squared over 0.750. And when we go through, we can just cross multiply. So take that Kb times 0.75, and then we'll take the square root of that product. And when we do that, what are we going to get? I don't have the answer here. But when we do that, we're going to get the concentration of that hydroxide ion, as well as the positive, the accompanying conjugate acid, so that other product there. When we do that, we're going to see that x is going to be equal to 1.8 times 10 to the negative 5th. And again, that's representing the hydroxide ion. So this is representing both of these. So then using that concentration, using that hydroxide ion concentration, we can use POH is equal to negative log hydroxide ion, and then we can use 14 is equal to pH plus POH. We're just going to rearrange that to be pH is equal to 14 minus POH. But we can use that to solve for the pH. And what we're going to see is we should have a POH of 4.74. So when we solve for the pH, we're going to see 9.26. And that answer, if we just think about it, makes sense. Just based on the KB, we should have a number somewhere around 10. Just because we've got 10 to the negative 10th as the exponent there. But also with the basic solution, that's what we're looking at here, the base dissociation constant. So we should have a pH greater than 7. So we can at least double check, make sure we're in the correct ballpark, and if that number makes sense based on what we're given in the question. Okay, and then looking at these two, why is sulfuric acid going to be a stronger acid than H2SeO4? So if we replace that sulfur with a selenium, why does that acid essentially become weaker with a selenium or stronger with a sulfur? And then similarly, why is nitric acid, so HNO3, why is it going to be stronger with that third oxygen compared to nitrous acid, which is just going to be HNO2? And in both cases, the answer is going to be very similar. It's going to be related to the electron density within these substances. In both cases, sulfur is going to be more electronegative than selenium. And then in the case of the nitrogen acids, the additional oxygen there is going to make that substance more electronegative. So it's essentially in both cases going to be able to pull electron density away from the hydrogen, just making it easier to dissociate. Which is just going to, if it's easier to dissociate, if we get more of that ion, it's just going to be the definition of a stronger acid in that case. And then with the final one, we've got two different pieces to this question. Excuse me. We've just got some diprotic acid. So we first want to think about what the dissociation equations would look like for that. And again, since it's diprotic, we've got two of the hydrogens there. We'll see it occur in two steps, and really this should be A2 minus, so we should have a -2 charge there. So it should be A2 minus. Same thing over here. But with it, we've got the Ka1, which is going to refer to the dissociation of that first hydrogen. Ka2 is doing the same thing in terms of the second one. And if we look at those values, times 10 to the -4th for the first one, times 10 to the -9th for the second one. So that first dissociation is going to occur at a much more readily by an order of 5 orders of magnitude. So when we're looking in terms of the pH of this question, or of this solution, we can really just focus on that first dissociation, because when we're looking at the hydrogen ion, both of these are going to give us H+, but that first dissociation is going to occur 10 to the 5th times more. So that's going to be what we're focused on. That's where we're going to get the vast majority of the hydrogen ion. So with the pH, we can essentially just focus on that first one. And we can do an ice table. We'll have 0.18 of that to begin with, 0, 0, oh, should be plus X for the products. And for this one, we could go through and plug in Ka1, so 3.4 times 10 to the -4th is equal to X squared over 0.18 minus X. So for this reaction, or this equation, a lot of the times we can remove that X from the bottom just because it's going to be a negligible change compared to the initial concentration. But in this case, Ka is 10 to the -4th, which is kind of right on the line of if it's going to be negligible or not. If it's not negligible, we have to keep that x on the bottom. We have to keep it in our denominator and actually cross multiply, get everything on one side in terms of x, do the quadratic formula. In this case, if we go through and do the quadratic formula or ignore it, we get essentially the same thing, at least to 2 sig figs. We get x is equal to 7.8 times 10 to the negative third. So in this case, it doesn't matter, but just with it, think about what that k value represents. And it's essentially telling us how far this reaction is going to shift one way or the other. Large numbers favor the product, small numbers favor the reactants. But with this number, it's not super small, like the previous one was 10 to the negative 10th. So this one's not quite as small, so it's getting pretty close to the line. So generally, if it's 10 to the negative third or smaller, definitely do the quadratic. 10 to the negative fifth or 10 to the negative third or greater, do the quadratic. 10 to the negative fifth or smaller, you can kind of ignore it. In this case, doesn't really make too much of a difference either way, but we just want to keep that in mind. But now we have that x value, so equals x, which represents H plus. We can solve for the pH. And what we're going to see if we actually do that, let me see what that's going to be. So negative log of 0.078. We'll get a pH of 2.11. And remember, with the pH, we pretty much only count the digits after the decimal is significant. So since we had 2 sig figs in that concentration, 7.8, we're going to want 2 digits after the decimal in our pH. That's why we have 2.11. And then for the second piece, I'm going to go ahead and erase all of this. And then for the second piece, if we want to actually get what this concentration is, and again, it should be A2 minus. We can kind of do the same thing. We can make another ice table. But in this case, we already know what the initial concentration of the HA minus is going to be. The same thing with the H plus, because that's what we just solved for here. So this is going to be another dissociation, but we already have some of the H plus. That's why we have that value already. We don't have any of the negative ion there though. So when we look at going through this, we can kind of have it like that. And again, I'm just using x to represent the 7.8 times 10 to the negative third that we just solved for, just so I don't have to write it a bunch. But now when we look at the Ka2 here, 10 to the negative 9th, this is a very small one, so even less of this reaction is going to go to the right-hand side. So with this one, what we can do is ignore the y for the reactant. We can also do the same thing for the product. Y is still going to be so much smaller compared to the x that we start with there, that it's not going to change that value at all, basically. So when we look at our equilibrium expression, we'll have Ka2 is equal to xy on the top for the products over x for the reactants, which is really just going to simplify to Ka2 is equal to y. So what we're going to see is the concentration of that that anion, A2 minus, is just going to be the same as the Ka2 value. So it's going to be 6.7 times 10 to the negative 9 there. And then with this, if you do have specific questions about any of this, let me know. Remember, there is practice problems in the textbook, as well as the chapter review just in Canvas, which has the answer key. But with it, if you do have questions, let me know. We can look at it during office hours, or you can bring those questions to class and we can look at them at the start of the class as well.